welcome you in the lecture series of random processes, detection and estimation. It is 16th lecture of the series. In the previous lecture, we have discussed about the matched filter and their properties. In this lecture, we will discuss about the generalized matched filter detector and its performance. And the outline of this lecture are the generalized matched filter detector, and after this we will discuss about the performance of the generalized matched filter and the signal detection in color noise. And in the objective of this lecture, you will able to explain when the generalized matched filter detector is used to detect the deterministic signal, and you will also able to explain how the signal can be detected in colored noise. Now we'll start with the generalized matched filter. The matched filter is an optimum detector for a known signal in white Gaussian noise. In many practical situations, the noise is more accurately modeled as correlated noise. The noise is assumed to have the PDF of normal distribution with zero matrix and with the covariance, and variance is the covariance matrix and mean is the zero matrix. And if the noise is modeled as wide sense stationary process, then the covariance matrix C has a special form of symmetric topology matrix. And when the noise are uncorrelated, the autocovariance function of the noise will be covariance of omega n. It will be equal to the autocorrelation of m minus at m minus n. So it will be autocorrelation function of the noise r w r omega tau. It will be equal to sigma square del tau. But for the non-stationary noise, the covariance matrix C will be an arbitrary covariance matrix. Now, for the performance of NP-decision rule, we perform the likelihood ratio test with the PDF under hypothesis H1 and PDF under hypothesis H0. So, NP detector decide H1 or H0 if the likelihood ratio means the ratio of the PDF under hypothesis H1 and the ratio of PDF under hypothesis H0 greater than less than the threshold value gamma. So the PDF under hypothesis H1 will be equal to 1 by 2 pi to the power n by 2 into 1 by determinant of the covariance matrix is to the power 1 by 2 and e is to the power minus 1 by 2 x minus s transpose C inverse x minus s. And the PDF under hypothesis H0, it will be 1 by 2 pi to the power n by 2 into 1 by under root determinant of the covariance matrix into e to the power minus 1 by 2 h transpose C inverse x. And the PDF under hypothesis H0, it will be 1 by 2 pi to the power n by 2 into 1 by the under root determinant of the covariance matrix e to the power minus 1 by 2 x transpose C inverse x, and where the covariance matrix C is equal to sigma square and identity matrix. And taking the log, we will have the log likelihood ratio test. It will be log likelihood function log E Lx will be equal to log E 1 by 2 pi to the power n by 2 into 1 by under root determinant of the covariance matrix C into e to the power minus 1 by 2 x minus s transpose C inverse x minus s. Here these x, s, c are in the matrix form. Divide by 1 by 2 pi to the power n by 2 into 1 by under root determinant of the covariance matrix C into e to the power minus 1 by 2 x transpose C inverse x, and this total likelihood log likelihood function will be greater than less than log E gamma. So I can write this expression as 1 by 2 x minus S transpose C inverse x minus S minus x transpose C inverse x greater than less than log E gamma. Or you can further express this expression as 1 by 2 x transpose C inverse x minus 2 x transpose C inverse S plus S transpose C inverse S minus x transpose C inverse x will be greater than or less than log E gamma. So you can also write it as x transpose C inverse S minus 1 by 2 S transpose C inverse S greater than less than log E gamma. Or further, you can reduce this expression to x transpose C inverse S, and we take this part to this right side. So it will be x transpose C inverse S greater than less than log E gamma plus 1 by 2 S transpose C inverse S, and this is the new threshold value gamma dash. So here the test statistic Tx, it will be x transpose C inverse S greater than less than new threshold value gamma dash. And for white Gaussian noise, this covariance matrix C is equal to sigma square by the sigma square into identity matrix. So I can write the test statistic as x transpose S by sigma square greater than less than the new threshold gamma dash. So here the detector test statistic x transpose C inverse S greater than less than threshold value gamma dash. So I can also write this as x transpose S is equal to summation n0 to n minus 1 x and Sn. This in the matrix form, this in the observed value form. So it will be greater than less than threshold value gamma double dash. Here the detector test statistic referred to as the generalized replica correlator or matched filter. And in the replica correlator, when the replica is modified as S dash is equal to C inverse S, then the test statistic Tx will be represented as x transpose C inverse S, and it will be x transpose S dash, because this part is you have modified as S dash, and this is the generalized replica correlator or matched filter detector. If the noise covariance matrix C is factorized as C inverse is equal to D transpose D, where D is an n by n invertible matrix, and the matrix D acts as a whitening transformation when applied to the noise omega, means the noise is assumed to be white, can be used after applying a suitable whitening transformation D. So since the expected value of omega dash, it will be the covariance matrix. So the test statistic, it will be x transpose C inverse S. It will be equal to x transpose, and C inverse means D transpose D. So it will be x transpose D transpose D S, and it can be written as x dash transpose S dash, where x dash is ds and S dash is ds. The pre-whitening form of generalized matched filter means the block diagram for the generalized matched filter as pre-whitener plus replica correlator of matched filter. You know, the test statistic Tx here is x dash t plus S dash, and this x dash t S dash, it will be equal to summation n0 to n minus 1 x dash n S dash n. Dash means you have done the pre-whitening process on the observed sample or on the signal sample. So the block diagram will be here. You have the data xn and apply the pre-whitening, so you will have x dash n, and then you have a signal Sn and apply pre-whitening, then you will get S dash n. So after taking the summation n0 to n minus 1 of x dash and S dash n, it will be the test statistic x dash transpose S dash, and this test statistic is compared with the threshold value gamma dash. When this is greater than the gamma dash, we will decide in favor of H1, and when this is less than gamma dash, we will decide in favor of hypothesis H0. To show that the linear transformation D, known as pre-whitening matrix, produce white Gaussian noise, let omega dash is equal to d omega. Then the covariance matrix means the expected value of omega dash transpose. It will be the expected value of d omega, omega transpose d transpose. So it will be d expected value of omega dash d transpose, and this is the covariance matrix C. So it will be d c d transpose, and you know C inverse d transpose. So d transpose d inverse d transpose, and it will be the identity matrix. So a linear transformation D is a whitening transformation, and generalized matched filter can be viewed as the pre-whitening followed by the replica correlator or matched filter, as you have seen in the previous figure. So now since test statistic is equal to x transpose C inverse S, or you can write it as x transpose S by C covariance matrix, and x transpose S is equal to summation n0 to n minus 1 x and Sn. So the test statistic, you can write it as summation n0 to n minus 1 x and Sn by sigma square. So the test statistic can be written as integration minus 1 by 2 to 1 by 2 xf sf conjugate divided by power spectral density of the noise. Here the PWW is the power spectral density of the noise, you know, and the whitening effect of C inverse is replaced by the frequency whitening, means 1 by power spectral density of the noise in the test statistic. Now let us one example. Let there are two hypotheses H0. This is correspond to Xn and it is equal to omega n, means under hypothesis H0 only noise is present, and under hypothesis H1 Xn is equal to Sn plus omega n, where small n is equal to 0 to n minus 1. Sn is known signal, and omega n is the normal random process with mean 0 and variance sigma n square, and omega n's are uncorrelated. Find the test statistic for the matched filter here. So noise are uncorrelated here, so the covariance matrix C will be sigma naught square 0 0 0 0 sigma 1 square 0 0 0 sigma n minus 1 square. So we will have the sigma square at the diagonal here because they are uncorrelated, and so the inverse matrix, the inverse of the covariance matrix simply will be the 1 by sigma naught square 0 0 0 1 by sigma 1 square 0 0 0 and 1 by sigma n minus 1 square. So at the diagonal we will have the value of inverse. So at the diagonal we will have the value of inverse covariance, and we decide H1 or H0 if the test statistic is equal to summation n0 to n minus 1 x and Sn divided by sigma n square greater than less than gamma dash threshold value. So it will be equal to summation n0 to n minus 1 omega n plus Sn by sigma n into Sn by sigma n. So you can also write it as summation n0 to n minus 1 omega dash n plus Sn by sigma n into Sn by sigma n. Here omega dash n, it is equal to omega n by sigma n. So where the noise samples have been equalized or pre-whitened. So the generalized matched filter is expressed as Tx dash is equal to summation n0 to n minus 1 x dash n s dash n, where x dash is equal to xn by sigma, or s dash n is equal to sn by sigma. This is here sigma n. Now the performance of generalized matched filter. The generalized matched filter decide H1 or H0 if the test statistic Tx it is equal to x transpose C inverse S greater than less than gamma dash, each using hypothesis test statistic in Gaussian since a linear transformation of x. The first two moments of the test statistic under each hypothesis are, so first we will take the expected value of the test statistic under hypothesis H0, it will be equal to the expected value of omega transpose C inverse S, and it is 0, and test statistic under hypothesis H1, the mean value of this test statistic will be the expected value of S plus omega transpose C inverse S. In this case, the noise is also present with the signal, and in this case I can write this as S transpose C inverse S, and the variance under hypothesis H0 of the test statistic, it will be the expected value of omega transpose C inverse S whole square, and it can be written as the expected value of S transpose C inverse omega transpose C inverse S. And because C inverse transpose will be equal to C transpose inverse or equal to C inverse. So here you can find out S transpose C inverse expected value of omega transpose C inverse S, and it will be equal to S transpose C inverse S, and the variance of the test statistic under hypothesis H1, it will be equal to the expected value X transpose C inverse S minus expected value of X transpose C inverse X whole square. So here you will get expected value X minus expected value of X transpose C inverse S whole square, and you will get here expected value omega transpose C inverse S whole square, and it will be equal to S transpose C inverse S, and this is the variance of the test statistic T under hypothesis H0. So as the white noise case, we can find the probability of detection, and it is Q inverse probability of false alarm minus D square. D square is the deflection coefficient, and the deflection coefficient will be the expected value of test statistic H1 minus the expected value under H0 whole square by variance under hypothesis H0, and it will give you S transpose C inverse S, because under the hypothesis H1 the mean value is S transpose C inverse S, and under hypothesis H0 it is 0, so it will be divided by variance of under hypothesis H0, it is S transpose C inverse S, so you will get S transpose C inverse S here. So the probability of detection will be Q inverse probability of false alarm, and the deflection coefficient here will be S transpose C inverse S, and covariance matrix C is sigma square identity matrix. So here The probability of detection increase monotonically with S transpose C inverse S, not with epsilon by sigma square in the case of white Gaussian noise. This is for the case of white Gaussian noise. In white Gaussian noise, the signal shape was unimportant. Only the signal energy are matter. Now here the signal can be designed to maximize S transpose C inverse S for the probability of detection. So here you can see that for the white Gaussian noise case, the probability of detection was Q inverse probability of false alarm, and the deflection coefficient under epsilon by sigma square for the case of white. Now signal detection in colored noise. Now we can explain the design of signal for optimal detection performance under correlated noise case. Consider an arbitrary noise covariance matrix C and signal S to be designed for the optimal detection. The detection performance can be optimized by maximizing the term S transpose C inverse S and by increasing the signal strength, but in practice this is the constraint because the signal energy, we cannot increase the signal energy from a certain limit. We cannot, and you know, S transpose C inverse S transpose is equal to the epsilon by sigma square, and epsilon is the energy of the signal here. So the optimal signal detection is chosen by maximizing the C inverse S transpose subject to the fixed energy constraint S transpose S is equal to epsilon. So use the Lagrangian multiplier. We want to maximize the term S transpose C inverse S plus lambda epsilon minus S transpose S, and lambda is some positive constant. Here C is the symmetric matrix, and after taking the first derivative of this F, we will get 2 C inverse S minus 2 lambda S, and so after putting the value of 0 of this first derivative, you will get C inverse S is equal to lambda S. So you can write here S transpose C inverse S will be equal to S transpose lambda S or lambda epsilon. S is an eigenvector of C inverse. So we should choose the signal S as eigenvector of C inverse whose corresponding value, that is lambda, is the maximum. So alternate since C inverse S is equal to lambda S from this, so we should choose the signal as the eigenvector of C, means Cs is equal to 1 by lambda S. So we should choose the signal as the eigenvector of C that has maximum eigenvalue, and if V minimum is the eigenvector associated with the minimum eigenvalue, then S will be under root epsilon V minimum. The scaling enforces the energy constraint since the eigenvector is assumed to be scaled to have unit length. Now let us take one example. We wish to design a signal for achieving the best detection performance in color wide sense stationary Gaussian noise with autocorrelation function ACF is equal to the autocorrelation function of the noise R omega omega k. It will be equal to P plus sigma square del k, where P and sigma are non-zero positive constant. The two computing signals here are S1n is equal to A and S2n is equal to A minus 1 is to the power n, where n is from 0 to 1. So this is the example which we have discussed in the previous slide. Now you have A greater than 0 and you have to decide which one of the signal would give the better detection performance. So two hypotheses are: under hypothesis H0, Xn is equal to omega n, means only noise is present in the under hypothesis H0, and under hypothesis H1, Xn is equal to Sin plus omega n, where Sin either of the given deterministic signal S1n or S2n, and omega n is the colored wide sense stationary Gaussian noise with autocorrelation function P plus sigma square del K, or the covariance matrix C P11 transpose plus sigma square I, where I denotes the n:1 column vector of ones, and I is n:1 an identity matrix. In case of detection of the non-deterministic signal in the colored noise, the detection performance of NP detector is completely characterized by the signal to noise ratio S transpose C inverse S. So the probability of detection will be Q inverse PF, and 1 minus under root S transpose C inverse S. This is the deflection coefficient, this square here, for the SNR, where the term is S transpose C inverse S denote the SNR. So the signal that gives the high SNR would resulting in the better detection performance for the given probability of false alarm. So to compute the resulting SNR for a given signal, we can have first compute the inverse of the noise covariance matrix. That there are two cases. First, when the length of the observation is even, means when n is equal to 2, and the length of the observation is odd, for example n is equal to 3. So we will consider the case first when the length of observation is even. So in this case, the inverse covariance matrix will be inverse of P plus sigma square P plus sigma square. So I can write it as the inverse of this. It will be 1 by sigma square 2p plus sigma square, and the matrix P plus sigma square minus P plus sigma square. So it is the inverse covariance matrix, and the SNR value for the signal S1 is S1 transpose C inverse S1, and it will be equal to 1 by sigma square 2p plus sigma A matrix, and matrix P plus sigma square minus P plus sigma square AA. Here it is S transpose C inverse S transpose S. This is C inverse S transpose. So it will be equal to 1 by sigma square 2p plus sigma square A sigma square A sigma square. So I can find out the value S1 transpose C inverse S energy of the signal S1. It will be equal to 2 A square sigma square by sigma square 2p plus sigma square, and it will be equal to 2a square upon 2p plus sigma square. And the SNR value for the signal vector S2, it will be S2 transpose C inverse S2. It will be 1 by sigma square 2p plus sigma square A minus A P plus sigma square, because for the case of S2 it will be A, and the signal was A minus 1 is to the power n. So it is A minus A, and the matrix P is sigma square minus P plus sigma square A minus. So you will have the value 1 by sigma square 2p plus sigma square, the matrix A minus A, and A into P 2p plus sigma square minus A into 2p plus sigma square. So we will solve this matrix as 2a square 2p plus sigma square divided by sigma square 2p plus sigma square, and it will be equal to 2a square by sigma square. So you have seen that for A P sigma greater than 0, S2 P transpose C inverse S2 will be greater than S1 transpose C inverse S. So in this case, the second signal or S2 signal having the higher SNR. And now for the length observation, when the length is odd, so C inverse will be inverse matrix of P sigma square P P P P plus sigma square P P P P plus sigma square. So the inverse of this will be 1 by sigma square P plus sigma square 2P plus sigma square, and the matrix 2P sigma square plus sigma to the power 4 minus P sigma square minus P sigma square minus P sigma square 2P sigma square plus sigma to the power 4 minus P sigma square minus P sigma square minus P sigma square 2P sigma square plus sigma to the power 4. This is the inverse of the covariance matrix. Now the SNR value of the signal vector S1, it will be S1 transpose C inverse S. It will be 1 by sigma square P plus sigma square 2P plus sigma square A 2P sigma square plus sigma to the power 4 minus 2P sigma square minus 2P sigma square minus 2P sigma square 2P sigma square plus sigma to the power 4 minus 2P minus P sigma square minus P sigma square minus P sigma square 2P sigma square plus sigma to the power 4, and S1 transpose, it will be A, and you can have 1 by sigma square P plus sigma square 2P plus sigma square A vector, and A sigma to the power 4, A sigma to the power 4, A sigma to the power 4, and you will get the value of this. It will be 3 A square sigma to the power 4 divided by sigma square P plus sigma square into 2P plus sigma square. And the SNR value for the signal vector S2, it will be S2 transpose C inverse S2. It will be equal to 1 by sigma square P plus sigma square into 2P plus sigma square, the vector A minus A, and the matrix 2P sigma square plus sigma to the power 4 minus P sigma square minus P sigma square minus P sigma square 2P sigma square plus sigma to the power 4 minus P sigma square minus P sigma square minus P sigma square 2P sigma square plus minus P sigma square and 2P sigma square plus sigma to the power 4, and the transpose of S2, it will be A minus A, and you can have 1 by sigma square into P plus sigma square into 2P plus sigma square, and the vector A minus A, and the matrix A 2P sigma square plus sigma to the power 4 minus A into 2P sigma square plus sigma to the power 4 into A and A into 2P sigma square plus sigma to the power 4. You will have the values 8A square P sigma square plus 3A square sigma to the power 4 divided by sigma square P plus sigma square into 2P plus sigma square. And again, for A, P, sigma greater than 0, you will have S2 transpose C inverse S2 will be greater than S1 transpose C inverse S1. Means, so the signal S2 gives better detection performance than the signal S1 in a given colored wide sense stationary Gaussian noise, whereas in white Gaussian noise case, in a previous lecture we have seen where either of the signal gives the same detection performance, but in this case the signal S2 having the high SNR value, so the signal S2 will give the better performance. So far in this lecture we have discussed about generalized matched filter, detector and their performance. Also we have discussed the signal detection in colored noise. This was the 16th lecture of the lecture series of random processes detection and estimation. In the next lecture, we will discuss the detection of the deterministic signal with unknown parameters. Till then, thanks for listening this lecture. Thank you.